Good afternoon, everyone. Welcome to the week 6 live interaction session of mathematical methods in physics. I hope I'm clearly audible. This is me, Biju Shah. I am a PhD PMRF research fellow at ISA Tirupati, and in this session I'll be discussing about the concepts that were discussed in the previous week, and also a few problems that will be helpful to you in solving the assignment problems. So let's begin with today's session. In case if you have any doubt in between, or if there is some technical glitch in the sharing of my screen or my problem with the audio, please let me know. Yeah. So I'll start with the recap from the previous class. In the previous class, I introduced a notation of expressing the differential equation in the form of an operator. So in this case, the operator I have denoted as a curly L. So that is the operator denoting the second order differential operator. Okay, and it operates on an unknown function, which is a function of x, and it spits out a function which is independent of y, and it's a function of only x. So in this problem, what I have is a function of x, yx, on which a differential operator acts, and that gives a function which is just a function of the independent variable, that is x. So we have known from the previous class that if my RHS, that is if is a function of just x, then that system of differential equation is known as linear differential equation. So if this capital F on the right hand side is just a function of x, or if it is a constant, then the differential equation is a linear differential equation. So throughout our lecture, we'll be focusing on linear differential equation. Now there are special cases, the subclasses we can say of this linear differential equation. That is when your capital F is equal to 0, then the differential equation is known to be homogeneous differential equation. But if f is the capital F function, if it is non-zero, then it is known as the inhomogeneous differential equation. So in the previous class, we have discussed briefly towards the end about the homogeneous second order differential equation. Remember, we wrote auxiliary equation and obtained the roots of the auxiliary equation, and comparing the roots of the two auxiliary equation that we got, we proposed 3 different cases, and using those cases we could write the solution of the homogeneous differential equation of second order. But in today's lecture, we will focus on how to arrive at the solution of an inhomogeneous second order differential equation. That is when your right hand side is not 0 but some function of x. Yeah. So this is how the general form of an inhomogeneous second order differential equation looks like. So there is a term. The first term is the a2d2 y by dx squared, that is the term containing the second order derivative, and the next term is containing the first order derivative, and the third is the a0y component. And my right hand side, as I said, is not equal to 0. It is a function of x, and that function, that right hand side, can be usually called as a forcing function, as we'll see later in today's class, that why it is known as something known as forcing function, because it has we can draw an analogy between a physical problem and to this certain class of differential equation. So for the time being, let us consider fx to be some function which is non-zero, and it is known as the forcing function. So given this particular function, given this particular differential equation, the solution can be written in sum of 2 terms. The first term will contain the complementary solution, and the second term will be the particular solution. Now what is complementary solution? Complementary solution is nothing but the solution to the homogeneous equation. That is the solution. If I were to write the complementary solution of this particular general form, let's say my yc is the complementary solution of this particular differential equation, then yc would satisfy the homogeneous version of this differential equation. Yeah. So YC satisfies the homogeneous version of the differential equation. And another term is the particular function. So that is something we will be focusing on how to arrive at in this particular session. So before moving on to how to obtain the particular solution, let me again give a brief recap of how to solve the homogeneous second order differential equation, because your total solution to any general differential equation is a sum of the complementary solution and particular solution. So in order to know the complete solution, it is important that you know both the complementary solution and the particular solution. Yeah. So the solution to the complementary solution is, as I already said, is the solution to the homogeneous differential equation. So we can write the differential equation in an operator form. That is, my capital D is d by dx, and I can factorize it and write it in a form given as this. Then this is known as my auxiliary equation. So d minus a into d minus v, that is written in factorized form. The roots of this will determine what will be my solution to the homogeneous differential equation. That is what will be my complementary solution. So there are three cases. We discussed this in the previous class. First case is the case of distinct roots. That is when your two roots are not equal, they are distinct. So A is not equal to B. For that case, the root of the equation, the root of the solution to the differential equation has this form. That it is like a linear combination of e to the power ax and e to the power bx. Okay, and next case is the case of equal roots. So the case of equal root is both of the roots of the auxiliary equation being equal. So in that case, the solution looks like this. So in every solution, you see there are two unknown constant, because it's a second order differential equation. So the A and capital B are the two unknown constants. And yeah, complex for the case when the roots are complex conjugate, so they occur in pairs. So alpha plus I beta is one root, and the alpha minus I beta is the another root. So that case gives the solution to be of this form, either in the exponential like Euler form e to the power I beta x, or in the form of cosine and sine. So yeah, the real part of the root appears in the exponential, and the complex part appears in the cosine and the sine part. So that's all with the homogeneous second order differential equation. Now let us I'll introduce some like formulation or some prescription that would help you to find the solution to what will be the particular solution. So using this few prescription, you can obtain the particular solution. So suppose your fx, so that occurred here, so the fx that occurred here has a form given by this. So this particular thing, if your fx is some constant k multiplied by e to the power cx, so if your fx has this form, then there are three cases arising. So first case is when the exponent occurring in the right hand side, that is the c part in the exponent, is neither equal to a nor equal to b. In that case, the yp takes this form. So this capital C is again an arbitrary constant that needs to be determined. This small c is something which you already know from the definition of this function fx. So you just need to compare whether the roots of the auxiliary equation, that is a and b, are they equal to c. If both of them are unequal to c, then the particular solution takes this form. Yeah. So then the next case is either of A or B being equal to C. So when either of them are equal to C, that time the particular solution takes this form. That is C some arbitrary constant C x into e to the power Cx. And when both of them are equal to simultaneously equal to B, that is all three of them are equal, so in that case you have Cx square e to the power Cx as a particular solution. Yeah. And the next category is the case where your fx is a sine function or a cosine function. So if it is sine alpha x or if it's cos alpha x, then you need to solve this particular equation instead. So when you see like this particular equation is nothing but equivalent to this particular equation, where your C is I alpha. So again you can come back to this case and check whether A equal to B or whether A is equal to I alpha or B is equal to I alpha, or none of them are equal. So depending upon the case, you can conclude what will be your particular function, the yp here. So when you see sine or cosine in the inhomogeneous part, you have to express it in terms of Euler form e to the power I alpha x, and then come back to here and check whether the exponents, the power I alpha is equal to A or B. Depending upon that, you write the particular solution and take the real or imaginary part. If you take the real part, if it is if it is cosine, and the imaginary part if it is sine. So yeah. And another next category that to deal with is you have a exponential is e to the power cx, but instead of a constant k, you have a polynomial, so which is itself a function of x. So that might occur in many number of times, that your k that occurred here is not a constant but function of x, like kind of it can be x itself or x square plus 2, any polynomial of degree n. So in that case, again there will be three criteria as previously we discussed. So in the first case, when like c is not equal to a and c is also not equal to b, so in that case it takes this form. So your Qnx is also a polynomial. So it is also a polynomial with the same degree as Pn. So you start with writing, let's say your Pnx is something like x square plus 2 thing. Then your Qnx yeah. So your Qnx would be again a polynomial of the same degree. So, and then what you do is you substitute both of them here. So you substitute Ecx into Qnx in this particular differential equation and try to find the values of these arbitrary constants a, b and c. You'll be able to recover one value of one constant and the other two will remain undetermined because it's a second order differential equation. So you can get the value of one of the constant. So likewise, similarly, when there are like three of them being equal, so then you have this x square e to the power cx into Qnx. So these are the like some special cases of differential like inhomogeneous differential equation where fx has this form, exponential form. So this will some prescription that might help you achieve the solution in a very quick time. So let's like take one particular case of among these various possibilities and see how do we solve it. So I have taken this particular case. So in here the fx is this. This is my fx. So before I go on to solve before I go on to obtain the particular equation, it is important that I know what are the roots of my auxiliary equation, right? So I would ask you to say me what are the roots of the auxiliary equation. Like if you can speak up or either type, then it would be better. So I'm doing it simultaneously. Okay. So this is what my auxiliary equation looks like. Sorry. Yeah. Yeah, so these are the roots of my auxiliary equation. So that says my complementary solution. So so in this case the roots are they're distinct and they are unequal. So e to the power x plus yeah. So this is the like the solution to the this is the complementary solution. Now let me go to find the particular solution. So for the particular solution what it requires is since this is a sine function, so you see this is a sine function. So as I already said, you have to express your sine function in terms of this exponential. So whatever occurs as the coefficient of x, you have to write here as a power of exponential. So that so in my case this alpha is equal to 2, right? So my equation now changes to yeah. So this is your new equation. Now you compare what are the roots, what are the values of the roots and what is the exponential. So clearly they are unequal. So 1 is definitely not equal to 2 and it is also not equal to 2i. So from that you can say that your particular solution will take this form, the form given here. That is yeah. So this is the form of a particular solution. So let us try to find out the some values. What will be the values of c and all? So dy differentiating once would give me and second differentiation would give me so let me substitute here all of them. So my y double dash is minus 4c e to the power 2ix and first derivative is this and next is minus 2y, that is minus 2 of c 2ix, and you're on the right hand side I have 4 yeah. So overall I have 6c e to the power 2ix So this is the value of C that I obtained. So my C is nothing but minus 3 plus I. So let's do some manipulation, that is minus 3 plus I and like minus 3 minus I, just to bring the exponential on the top. So that would give me, yeah, so this is what C is. So my y particular is C e to the power 2 ix, that is minus 1 by 5. Yeah. So since this is a sine part, so what I have to do is I have to take the imaginary part of this entire solution. So yeah, so imaginary part of y particular would be uh, minus 1 by 5 cos of 2x plus 3 sine of 2x. So this is the required solution for the required particular solution for the above differential equation. So the total solution would be the solution, complementary solution, as well as the particular solution that we obtained. So your complementary solution was aex plus b e to the power minus 2x. Yeah. So this is a complementary solution, and your particular solution was so this is your entire solution to the differential equation. So there are two unknown constants, and because it's a second order differential equation. Yeah. So I hope this is clear. So the main spirit of the problem was you had to know the roots of the auxiliary equation and then compare with the root with the coefficient present in the sign part, and depending upon that you have to write your format of the particular solution and then get the value of the unknown constant C, and the particular solution along with the complementary solution is the total solution to the differential equation. Yeah. Yes. Now let us come to another topic. So in this in the previous topic we discussed when fx has certain specific form. So it was mainly based upon exponential raised to some power of raised to x. Okay, but had your the fx was any general function, so how would your approach be? So the main approach is to look at the form of the fx and propose some solution, like assume some solution, and then put the assume some solution of the particular equation and put it in the differential equation and get the values of various unknown constants. So the next part is based upon where your fx or phi x can be any function in general. So let us look at a few cases like that. So first case is when your function is a polynomial. so there is no exponential involved here, it's just polynomial. So it's a polynomial of nth degree. So in that case, the motivation would be to assume the particular solution yp to be also a polynomial of degree n. Yeah. So I have assumed a polynomial of degree n here. So next case is this particular case that we already discussed. So it has the exponential form. So a to the power alpha x, and the next case is e to the power alpha x multiplied by some polynomial. So we write e to the power alpha x multiplied by the some nth degree polynomial. Another case when your fx is like involves sine and cosine. So in that case, what we can do is we can assume a solution that is a sine beta x plus b cos beta x, and then determine a and b. So this is how we can like another way to approach at the particular solution, that is to assume a solution and arrive at the necessary values of the coefficient, that is a and capital A and capital B. So with this motivation, let us go towards solving this particular problem. So in this case, what you see, the right hand side fx, it is a polynomial. It's a cubic polynomial of degree 3. So that motivates my particular solution to be a cubic polynomial, right? So yeah, so this will be my proposal for the particular solution. So before moving on to finding the particular solution, let us again look at what is the solution of the homogeneous equation. So the solution to the homogeneous equation, did my screen sharing stop? Or just hold on for a second, there is some network issue. Yeah. I hope I'm clearly audible right now. Yes. Okay. Thank you for confirming that. Yeah. So what I said is, since my fx is just a cubic function, the motivation was to start with a particular solution which is also a cubic polynomial. So before deriving onto deriving the values of capital A3, A2 and A1, so let's first of all write what is my the solution to the homogeneous equation. So the solution to the homogeneous equation, in this case is this. Yeah. So these are the roots of the auxiliary equation. So they appear in complex conjugate pairs with the real value of the roots. So if it is lambda 1 and lambda 2, so the real value of lambda 1 is 3 uh, lambda values, and real values of lambda 1 or lambda 2 is sorry, so imaginary value of lambda 1 or lambda 2 is 4. So the complementary solution has this forms. E to the power 3 2, that is c1 of cos 4t, and then c2 of c2 into sine 4t. Yeah. So this is what your complementary solution is. So let us now go on to find this particular solution. So the first derivative would be yeah. So we substitute this all in the differential equation. So this was my differential equation. So it is first I have to substitute this 6a3t plus 2a2, then minus of 6 into this first order derivative, and then plus 25 of the y itself. And this, it's equal to this 50t cube yeah. So now let me separate out various powers of t and then compare on the from the both sides. So first of all, I have this 25a3 with t cube. Now my t squared terms are 25a2 plus minus of 18a3. That's all with t square, and with t I have 6a3 then I have this minus 12a2, then plus 25a1, and the remaining terms are with t0, that is 1. So the remaining terms are my 2a2 and minus 6a1 and 25. So there is this, sorry, I made this mistake here. So it is a0t. a0, just a0. So that is 25 a0. So this is equal to this particular thing. Yeah. Now comparing various powers of t, the coefficients of various powers of t, what you get is first of all 25a3 is equal to 50, that is one equation you get, and then next equation is 25a2 minus of 18a3 is equal to minus 36 is the second equation. Then comparing powers of t is and the last one is the constant. So you have mainly 4 equations and also 4 unknowns. So from the very first equation you can easily get a3 is equal to 2, and then substitute a3 here and you can get a2, and then whatever a2, suppose you get some a2, you substitute here and here and obtain a1. Likewise you can get a0 also. So I'm directly writing the results. So your a3 that came out to be 2, your a2 is equal to 0, and your a1 would come out to be minus of 3, and a0 is equal to 0. So what you have mainly done here is you have obtained the values of various coefficients that appeared in the particular solution. So this was your particular solution and you have got all of this. So with that I can write my particular solution to be 2t cube minus 3t. So all other powers of t vanishes because coefficients are 0. So my total solution is then sum of complementary solution and particular solution. So complementary solution was e to the power 3t into c1 of cos 4t and c2 of sin 4t. And now your particular solution is this. So c1 and c2 are two unknown constant, arbitrary constant that can be determined if initial conditions are given. So overall this is the solution of the differential equation. So we started with an assumption and then we found out the values of the coefficients. So that's what we did in this. So with that, let us move to another technique of solving a second order inhomogeneous differential equation. So that is known as the variation of parameter. So variation of parameter, remember we started with solving the homogeneous first order differential equation. In the previous lecture, I said that if your linear differential equation has the form which is given by, let's say, dy dx plus px y is equal to qx, then essentially you have to find something which is the integrating factor e to the power of px dx, and your solution takes this form. Yeah. So this is how the solution of a inhomogeneous first order differential equation look like. So let us have a brief review over that. So if your first order differential equation is homogeneous, then using the technique of variable separation, this would be your solution. So here actually that A is an arbitrary constant. Arbitrary constant, because this is a second order differential equation, so you have one arbitrary constant. So when you allow it to become a variable, so let's allow that A to become a variable, that is now your A is also a function of x. So with this, if you demand that this to be a solution of the inhomogeneous equation, so ultimately we are trying to find the solution of this inhomogeneous equation. So instead of 0, it is a function of qx. So when we demand that this particular expression is a solution of an inhomogeneous equation, so we substitute it here. So when we substitute it here, we get ax to be of this form, that is the arbitrary constant in the inhomogeneous differential equation. Arbitrary constant in the homogeneous differential equation A, we allowed it to become a variable and demanded that this solution as a whole is a solution of the inhomogeneous differential equation. So when we demanded that, then it led to a constraint on ax, that your ax has to be of this form, that is qx is present here, and in the exponential of e there is integration of px dx. So that is a constant on ax. So overall we have yx to be the solution to the inhomogeneous first order differential equation is this. So we can do some manipulation and we get to see that this is what we discussed in the last class. So we had this particular expression discussed in the last class. So let us generalize this particular method, the very same method, that is allowing an arbitrary constant present in the solution of the homogeneous differential equation to become a variable would drive us towards the calculation of the solution of the inhomogeneous equation. So this is the notion that we are going to generalize for the second order differential equation, and that is what is known as the variation of parameter. Variation of parameter, because we are allowing the constant to become a variable. So let us start with this particular second order differential equation. So this is a linear inhomogeneous second order differential equation, and the homogeneous version looks like this. The RHS is equal to 0. So like as we do it for homogeneous differential equation, we can write the auxiliary equation and get the roots, and then we can write it as a linear combination of two particular solution, two complementary solution. So the linear combination, the coefficients are arbitrary constant for the homogeneous version, but when we allow them to become a variable, so now my C1 becomes a variable, that is a function of x. C2 also becomes a variable, V2, which is a function of x. And then we demand that this particular solution is a solution of this inhomogeneous equation. So that is what our demand is. Obviously then it would put some constant on V1 and V2. So mainly we have to find what is V1 and V2. So provided we get to know what is my V1 and V2, I can easily obtain my entire particular solution. So that is what the motive is. So let's explore this method by applying it to some differential equation. So the differential equation I have in hand is given as this. So this is the differential equation I have. So this is a linear inhomogeneous second order differential equation. So the homogeneous version, so we need to write the homogeneous version. So if you can say me what will be the homogeneous solution to this. So first of all, let's write the auxiliary equation. The solution to the auxiliary equation is so these are the roots of my auxiliary equation. So they are complex conjugate pairs. So the real part here is 0. So that is why there is no exponential remaining. So real part of d is 0. So only this sum of sine and cosine we have. So this is my complementary solution. Now my objective is to make them, both of them, function of x. So we propose this. We propose that a particular solution of the inhomogeneous version has this form, that is yeah, it has this form. So let me find out the first order derivative of this. Yeah. Now the way to go about is this, is to choose my v1 and v2 such that these two terms vanishes. So dv1x ddx of v1 into sin x plus ddx of v2 into cos x equal to 0. So when we impose this particular condition, so my ddx of yp becomes v1 cos x minus v2 sin x. So we have one more restriction on v1, that is here. So this is right now, after imposing this restriction, this is my first derivative of yp. Now the second order derivative would be yeah. So this is my second order derivative. Now we substitute them in the original equation. So my original equation was this was my original equation. So substitute this. First term is and y is given as v1 sin x plus v2 cos x, and I have sec x into tan x. Yeah. So this and this cancels, and this also cancels. So we have dv1 dx cos x minus dv2 dx sin x is equal to let's write it to be sin x by cos squared x. So this is one more constant we get on v1 and v2. So from this particular constant, let's name it 1. So we will use 1 and 2 to get v1 and v2. So from 1 what we see is dv2 dx is equal to minus of dv1 dx sin x by cos x. So I'm just using my equation 1 here to write dv2 dx in terms of just v1 and sin x cos x. So that's what I did here, and this is what I get. So let's put this in 2. Yeah. So what you have is, so it's basically cos square x plus sin square x and cos x here. So your dv1 by dx is equal to sin x by cos x, that is equal to tan x. So now it's basically you have to just integrate tan x dx. So this is standard integration, which is given by this. So this is your v1, we got v1. So right now let's use this to get my v2. So putting this in 3, so your dv2 dx is equal to minus dv1 dx. So dv1 dx is tan x, so minus tan x sin x cos x. So it is mainly tan square x, right? Yeah. So it is tan square x. So your v2 is integration of tan square x dx. So that is nothing but integration of 1 minus sec square x dx. So you have x here, and then integration of sec square x is tan x. Yeah. So thereby we have obtained both v1 and v2. So we can write my the complementary solution was the particular solution was v1 sin x plus v2 cos x, like it was of this form. So what we got is ln of sec x into sin x plus so it's x cos x minus sin x. So this is my yp, and your yc was c1 sin x plus c2 cos x. So total solution can be written as this. So this is how we have obtained the particular solution by using the variation of parameter. So what the main change or the main point was to make the arbitrary constants appearing in the solution of the homogeneous equation to become variable. So by doing that we could arrive at the particular solution. So this was with variation of parameter. Now let us look at some application of second order differential equation in physics. So this simple harmonic motion, like the form here is that it appears that there is a spring attached to a mass m. the spring constant of the spring is K and the mass of the block is capital M. So when we displace the mass by a certain displacement, let's say x is the displacement, so what happens is there is a restoring force uh, like acting on the block that tries to pull back the mass back to the same configuration, same position. So that acts in this opposite direction, opposite to the direction of where the mass was displaced. So when we write the Newton's law of motion for the mass block M, so what is there? There is this acceleration term, and then there is minus kx, minus because it is acting in the opposite direction. So on the right hand side I have minus kx. So the Newton's law of motion for this particular case of the spring mass system is this very simple looking equation. So this is a case of undamped equation, so undamped condition. So undamped condition means there is no damping in the system. So damping can arise due to various reasons, like in every practical scenario there is damping due to air resistance, damping due to, let's say, if the mass is dipped in a viscous liquid, then there will be damping due to the viscosity of the liquid. So all these such cases of damping might arise, but this is a very ideal scenario that there is no damping present. So in that particular scenario, the equation looks like this form, the equation of motion. So can you please say, like, this is whether this is inhomogeneous or homogeneous? So yeah, clearly this is a homogeneous equation because there is on the right hand side it is a constant. So right now let's then how to solve the equation of motion. So the equation of motion can be obtained. First of all, we rewrite it in this form, then we define some omega. So omega will be the frequency of the oscillation. So this is the frequency of oscillation. So that is equal to root of the spring constant divided by the mass. So this is how the modified equation looks like. So now the next question is how to solve this particular category of differential equation. So this is the homogeneous second order differential equation. So obviously the way to go about this is to find the auxiliary roots of the auxiliary equation. So this is my auxiliary equation. So the root is given by this. So this is what the equation of the displacement x is a function, how it varies with time can be studied from here. So it is a e I omega t plus b e to the power minus I omega t. So now let us introduce some damping term in the equation and see how the equation changes. So I have introduced this damping term here. So this is my damping term. So the damping term is a function is proportional to the velocity. So dx by dt is my velocity and L is the damping constant, we can say. So since the damping motion also tries to oppose the acceleration, so that is why it appears with the minus sign here. So we can rewrite this equation again in this format. So here what I have done is I have assumed that 2b to be equal to L by m, and my omega square is equal to k by m. So this is the substitution I have done, and I have obtained this particular form. So again this is an homogeneous equation, right? So this is again an homogeneous equation. Yeah, this is again an homogeneous differential equation. So let us look at various possibilities. Okay, depending upon the value of b and omega, which of the cases we should consider. So there were three cases depending upon the roots of the auxiliary equation. So let us check all of these cases. So I'll quickly go through this. So first of all, I have this is my auxiliary equation. So the roots would be given by this. So now let us consider various cases. Okay, so case 1 is where your b square is less than omega square. So in this category would mean that the roots are appear in complex conjugate pair. Yeah. Yeah, roots are appearing in complex conjugate pairs. So what we can define is, let's define a beta to be omega square minus b square. So this is real, this part is real. So now right now my roots are minus b plus minus I of beta. So this is my real part and this is my imaginary part. So my xt is e to the power of minus bt a sine beta t plus b cos beta t. So this is a case of underdamped motion. So this case 1 is underdamped. Yeah. So for this case, the motion is oscillatory. There is also some kind of damping involved, but since the damping coefficient, that is b, is much lesser than this omega, so the damping does not affect much. Does not affect the oscillatory motion much. So we can say that for the case of underdamped motion, the motion of this block is almost, the motion of this block continues to be oscillatory for the case of underdamped motion. The motion is oscillatory. Now other two cases are when b becomes equal to omega and when b becomes greater than omega. So we will discuss these two cases more. Yeah. So first of all, let us look at the case when b is equal to omega. So when b is equal to omega, so the roots become equal. Right? So your so xt yeah so the roots become equal and they are minus b. So your xt will have this form. Yeah, so that's all for this scenario. So here the motion is just oscillatory. So like if you slightly move away from this like increase your b, so if you just increase your b and b becomes greater than omega, then it will immediately move to the case of underdamped, and if you just slightly decrease b, then it will immediately go to this category of underdamped motion where it becomes oscillatory. So this critically damped is the case of just being oscillatory. So this one is just oscillatory. It creates a distinction between two cases where underdamped and the overdamped. So when you suppose the next category is where b square is greater than omega square. So in this case, what you have is b square to be greater than omega square. So this particular thing is real. So you have distinct roots. So they are not in complex conjugate pairs since both of them are real and they are distinct. So yeah. So these are the two roots. So you can define some variable, let's say b to be this. Yeah, so that would say this particular thing is your minus lambda, and this particular thing is your minus of mu. I have defined this because you see, like lambda and mu are always greater than 0. So you see both of them are greater than 0. So that would say the roots are always negative. Definitely roots are real, but they are also real and negative. So that makes it very apparent. So roots are real and negative. So you can write yeah. So since your lambda and mu are like positive, so obviously from this equation you can conclude that this is an exponentially decaying motion. Yeah. So what happens is this, for this particular case you displace the block by a slight like let's take a displacement x, and if your b square happens to be greater than omega square, then the motion becomes underdamped, that is the motion becomes overdamped. So with time it comes back to its original position and it just stays there. So it doesn't oscillate about its mean position. It like just stops at certain position. So the oscillatory motion is not present in the case of this overdamped scenario. So with all this condition in mind, so let us go about solving this particular problem. So what is here basically is you have values of this various constants given, and you have to determine whether the motion is periodic or oscillatory. So that would be known if from the values of b and omega. So and also find the value of the force that will make the motion critically damped. So basically you have to make b equal to omega and come at some condition of the force, and also you have to find the expression of the displacement at some time t. So let us do this problem. So this will be a bit interesting also because it has some connection with the physical world. So basically the equation of motion, first of all let us write here. So let this part is equal to my 2b, and this part is omega naught square. So from the first question, so this is the thing we have. So from the first question, what we have is the mass is 10 gram and it is acted upon by restoring force something 10 dynes per centimeter. So some restoring force 10 dyne per centimeter and resisting force 2 dyne per centimeter. So from here what you have is that your value of K, which was the restoring force, so the restoring force is 10 dynes per centimeter, and your resisting force, yeah, this is your resisting force, that is your value of L. Yeah. From the like, obviously this has to be of unit of second centimeter. Yeah, so this is 2 dynes second per centimeter, so that is my restoring resistive force, and this is my restoring force. So let us put this and we get the value of B immediately. So B is equal to 2 of this. So from here you have B is equal to 0.1. So now again let's calculate what is my omega naught here is. So omega naught is K by M. So your K is 10 and M is 10. You get 1. So from here what do you see is B is less than omega naught. So can you say whether this motion, does it belongs to under damped category or over damped category? So B less than omega naught, so your resistive force, the resistive force is less than your the frequency, or it's a synonym of restoring force. Yeah, so since the, yeah, absolutely correct, so your resistive force is less than your restoring force, that would say that the motion is under damped. So that says your motion will be oscillatory. It will be oscillatory in nature. So now let us go to the second part. So in the second part it was asked that what will be the value of the resisting force, that is what will be a suitable value of my L such that B becomes equal to omega naught. That is the case of critical damping. So this is the case of critical damping. So we have to arrive at what is the value of L. So my as I know my B is L by 2m, and omega naught is root of K by M. So that would say L square is equal to 4m square K by M. So my L is equal to 4km root, that is so your K is yeah, your K was 10, M was 10, it is 20. So if your this resistive force is equal to 20 dynes second per centimeter, then you achieve the critical damping scenario. So that is what you have to find. And let us quickly move to the third question. So in the third question what you have is suppose the mass is given an impulse of this quantity like 20 gram centimeter per second while it was at rest. You have to obtain the expression for the displacement. So since if we start with this parameter, that is this parameters of k and l, we have already concluded that my motion is oscillatory since b is less than omega naught. So that allows us to write this particular solution. Yeah. So this was in the we have solved. So how did we arrive this? We arrived it by solving the auxiliary equation and getting the roots. So this was in the real part, and this particular is in the was in the imaginary part. So yeah. So this is how the general solution look like. So but we are given with some information, some initial condition, as I was saying earlier, with using which we can get A and B easily. So first of all, it's at time t is equal to 0. It was at the origin. So the mass was at the origin at time t is equal to 0. So that says if you put t equal to 0 everywhere, what you get is A is equal to 0. So you obtain xt as yeah. So now you can obtain the b by considering the velocity condition that was given. So let us calculate the velocity. So dx by dt would be the velocity. Yeah. So from the question what you have, from the question you have that at t equal to 0, velocity was equal to v0, and this was achieved by giving an impulse force. So the impulse that was given was 20. So it was written here that the impulse was 20 gram centimeter per second. And we know impulse is nothing but change in the momentum. So before the impulse was given and after the impulse of event, change in the momentum. So this was the final. After the impulse was given, it achieved a velocity v0. But before the impulse was given, it was having no momentum. So it was completely at rest. So that is why it is 0. So this is equal to 20. So this gives me that v0 is equal to 20 by m, that is 2 centimeter per second. So I even got the value of v0. So what I do is, so at t is equal to 0, your dx by dt is equal to v0. So I put t equal to 0 here, and what I get is, so this term goes away. I only have v0 is equal to yeah. So this is all I have. So my b is equal to v0 omega square by b square. So what is your omega square by b square? It is so we earlier calculated omega was 1 and b was 0.1. Yeah. So what I get is this particular thing, yeah, root of 0.99. So with all this, what I get, b is equal to v0, that is 2 by 0.99. So let's put all of this in the solution. So this was my solution here. So putting B is equal to this 2 by 0.99 e to the power minus of B. So my B was 0.1 sine of omega naught square by B square was point root of 0.99 t. Yeah. So this is what is the solution looks like. So what we have achieved is we achieved the how to obtain the value of position given at any time. You just need to input the value of time and you obtain the value of the position. Yeah. I hope that was clear. So let us come to the next case, which is forced vibration. So far there was no external force that was being given to the system. It was just the inherent restoring force and some impulse being given in the very first hand, but there was no continuous force which were being fed to the system. So let us come to a case where there is some driving force present. So the driving force essentially keeps drives the motion. So that occurs in this right hand side. So it is with a plus sign because it helps in driving the motion, unlike these two terms. So these two terms like dams the motion, like it restores the motion back to its original position, and it also like prevents the block from moving. The damping term does that thing. But let us add another term which is some function of a cosine function of t. So this periodic function gives some like it keeps the motion on, like it keeps the motion period like oscillatory. So for that particular situation, so we can say that this is a case of inhomogeneous differential equation, because my right hand side, the right hand side is not equal to 0, unlike the other cases. So to solve this equation, again we have to first of all know the solution to the homogeneous differential equation, and we can perform any kind of method that we learned earlier in this class to get the value of the particular solution. So one is the method of undetermined constant, that is looking at the form of the in like this fx or the phi x, if we say, then we have to propose the solution and get the value of c and d. So given this equation, let's take the particular solution to have this form. Okay, so when we assume that this is my solution of the inhomogeneous differential equation and put my first order and the second order derivative on the left hand side and as well as on the right hand side, then we arrive at some condition on c and d, that is the constants, the arbitrary constant that appeared here. So they are no longer constant, they are functions of t. So yeah, this is what we obtained, c and d. So the total particular solution, like once we substitute c and d here and perform some mathematical manipulation, so this is how the resultant particular function looks like. So this part is the amplitude, this very part is known as the amplitude of the function, and this is the phase factor. So the phase factor is given by this. So phi is equal to tan inverse of this entire thing is the phase factor, and this is the amplitude. So xp is equal to so one part is the amplitude and another is the phase. So for the condition of resonance, resonance is a condition where the amplitude of the motion becomes very high. So that can be like as we keep on increasing this driver frequency, we can achieve that condition. and for a particular value of this driver frequency omega naught, we get to see a peak in the amplitude. So basically we have to find at what omega naught if becomes maximum. So that value of omega naught would say that the system is in resonance. So that is being done by taking the first order derivative, set equal to 0, and the condition for the resonance is given by this. So this is where the amplitude becomes maximum. So basically here what you have when you look at it is root of omega square minus 2b square. So when the frequency of the oscillation becomes equal to this particular value, so that time the amplitude reaches a peak, and this particular value is omega is nothing but root of k by m. So k was something to do with the the spring constant, and b was with the damping force. So basically when your the frequency of the period of the driving force, that is frequency of the driving force, becomes equal to this root of omega square minus 2b square, at that point there is a peak in the amplitude. So that is known as the resonance frequency. So whether resonance can be achieved or not can be understood by looking at this. So if this particular terms comes out to be imaginary, so the resonance is not achievable. So it is only achievable only when omega square is greater than 2b square. So let us look at a very simple problem. So this is the problem we have in hand. So from here what we see is we have given with this equation, and we are asked to find determine whether it can be resonantly tuned or not, and if it can be resonantly tuned, what is the resonance frequency associated. So here we have, if we compare the two equations, so we have 2b is equal to 8, so that would say b is equal to 4, and omega square is equal to 36. So let us check this particular condition. Is your omega square greater than 2b square? Is this condition is satisfied? So 36 is greater than, so as 36 is greater than 32, that would say that it can be resonantly tuned. So now the next question is, what is the resonance frequency? So resonance frequency is nothing but given by this. So so your resonance frequency is 2. So that says that if your driver force, that is f of t, is equal to f naught cos of 2t, so if this ft takes this form cos of 2t, then for those particular values of b and omega, that system would be in resonance, that is the amplitude will reach a peak. So that's with the case of this particular system, which is the spring mass system. So let us do similar analysis for the electrical circuit. Okay, so this electrical circuit I have considered is an LCR circuit or RLC circuit. Okay, the F in the F cos 2t is an amplitude of the amplitude of the driving force. So it is an amplitude of the driving force, just like here we have as the amplitude, some amplitude associated to the motion. So F is the amplitude of the driving force. So let's take capital F T. So it is sinusoidal in nature. So this height is my small f. It is the maximum value of the driving force. Okay. Yeah. Let us perform a similar analysis for this particular electrical circuit. So this is an RLC circuit. So there is a resistor component, there is a capacitor, and there is a inductor. Okay, and it is being connected by an AC power source. So the AC power source is has this form E naught sine omega t. So the differential equation of this particular system, that is differential equation governing the current flow, is this. So this is the voltage difference across the inductor, across this component. This is the voltage difference across the resistor, and this is the voltage difference across the capacitor, and this is my input voltage. So you can draw an analogy between this particular situation and the earlier spring mass system. So here the driving force is this. Okay, so this is my driving force here. So E naught is the amplitude of the volt power source, and overall with time it varies sinusoidally. So what our main motive is to perform a similar analysis that we did for the spring mass system and achieve at the condition of the resonance. So what is the resonance condition for this particular system? Yeah. So starting with our equation, so in order to get rid of this differential equation, integral equation, so right now it involves both integration and differentiation. So just to get rid of this integration, what we do is differentiate once again this equation with respect to time. So when we differentiate with respect to time, yeah. So this is what we are left with. So again we will use the method of undetermined coefficient and propose that my particular solution, that is, let's take IP as a particular solution, assume that IP to be this, same as we did for the spring mass system. So once again perform the differentiation twice. So you put all of this here in this equation. Putting all of this in equation 1, and then what you do is you compare the coefficient of sines and cosines. So you see the right hand side, it involves only cosine part, there is no sine part to it. So after putting this and this here and equating coefficient of cosine, what we get is uh, yeah, so E naught omega was appearing here, so that is this, and this is the coefficient of cosine. Now the sine part, since there is no sine term on the right hand side, this sine term is equal to 0. So now let me introduce one important parameter that you see in these two equation, that S is equal to omega L minus omega C. So this is something known as reactance. Yeah. So this quantity in electrical circuit is known as a reactance. It is omega L minus 1 by omega C. So with this replacement, we can rewrite these two equation in this form. So R is my resistance and S is the reactance. It is the the resistance offered by the inductor and the capacitor. So this is my main form what we have. Then on solving this, we can get A to be equal to and B to be equal to this. Yeah. So having obtained A and B, so let's put it here. So my particular solution is now yeah. So that is so I have taken E naught by root of r square plus a square as my common factor. So I am left with this. So define this to be cos theta and define this to be sin theta. So when you do this, you have so cos theta sin omega t sin theta cos omega t. So you have written this as sin omega t minus theta with where tan theta is equal to your this sin theta by cos theta. So that is basically S by R. And let's also define the amplitude to be I0 by root of r square plus I0 is equal to E0 by root over r square plus a square. So with this we have the particular solution to be given by this. Yeah. So what you see a direct analogy between this and what we derived earlier in the spring mass system. So having derived this, let's also find the complementary solution to this, equation. So complementary solution is these things being set equal to 0. So you have this R by LD plus 1 by LC I is equal to 0. So the roots of the the auxiliary equation would be minus R by 2L plus minus root of R square by 4L square minus 1 by LC. So I'll solve the quadratic equation, and this is what is a root. So they are real and distinct. So what you have is minus of alpha plus minus the beta term. So let this be alpha and this entire thing be beta. So since the roots are distinct, so what you have, your complementary solution to be given by C1 of this and C2 of this. Yeah. So again you see that the roots are clearly negative. So you see the roots lambda 1, it is basically minus R by 2L, and the next term is from the R by 2L some other term is subtracted. So this thing is obviously less than R by 2L. So that says that both lambda and lambda 2 is negative. So what happens to this then? So as t is tending to 0, as t tending to infinity, so as you increase the time, so what happens is IC, it decays exponentially and it becomes equal to 0. So that is what is the condition of steady state. So as the steady state is reached, the IC part goes to 0, the complementary part of the solution goes to 0. So there is no exponential dependence. The only part that survives is this this oscillatory part. So exponential decaying part, it decays with time. Only thing that survives is the oscillatory part. So this is the steady state solution. So right now we are interested in finding the resonance condition. So the resonance condition would be given by the condition where the I naught part, the amplitude, reaches a peak. So what I define my I0 to be, I0 I define to be this. So this is what I define my I0 to be. And let me substitute what was my S. So my S was omega L minus 1 by omega C. So I0 will go peak when the denominator part decreases. So denominator part will decrease when omega L minus omega C goes to 0. So that says that for omega is equal to 1 by root of LC, at this particular case, that is the I naught, it reaches a maximum. So the resonance condition is given by one by root of LC. So the thing is, like if your driving frequency, that is your this particular omega is 1 by root of LC, at that point the resonance, the current in the circuit would reach a peak. So that is what is meant by resonance in this. So another thing also that is mainly important in electrical circuit is the resonance condition. This is the current resonance condition. So this is where the current in the circuit would reach a peak. So another resonance condition is the voltage resonance condition. So this is a condition where the voltage across the capacitor reaches peak. So since we have obtained the current in the circuit, the voltage across the capacitor would be the current into the resistance from the capacitors. So capacitive reactance. So for the case of this non-linear elements called, so resistor is a linear element, it's an ohm device, but capacitor and inductor, they are not linear element. So what we use the term is the reactance in terms of resistance. So the voltage difference across the capacitor is given by current flowing, that is my E0. So this is the peak value of the like not the peak value but the amplitude. So this is the amplitude of the voltage. So we take the amplitude of the current, that is R square plus omega L minus omega C square. So this was the amplitude of the current. So I have written this amplitude of the current, and the amplitude of the voltage is equal to amplitude of the current into the capacitive reactance. So capacitive reactance is given by this. So omega L is the reactance across the inductor. The reactance across the capacitor is 1 by omega C. So this is the voltage, amplitude of the voltage across the capacitor. Okay. So we have to find where BC, this VC reaches peak. The amplitude, it reaches a peak. So obviously the denominator has to be like minimum again. So we have VCA is equal to, so we can bring everything inside and we can write this omega square C square R square. Yeah, we can write this. So we want the denominator to be minimum. So denominator to be minimum, we need at what value of omega denominator is minimum. So right now we can't just make this equal to 0 and say that denominator is minimum for that particular value of omega, because omega is also involved here also. So what we do is we take the first order derivative of this entire function, and set it equal to 0. So yeah. So one is omega is equal to 0. So this would correspond to a different scenario, but we are interested in the denominator being minimum. So that would correspond to this being equal to 0. So that is the condition is, yeah. So this is the condition for the voltage across the capacitor to reach a peak. So this is another resonance condition. So we have obtained earlier omega dash to be LC. So this was my current resonance condition, and this is my voltage resonance condition. So we see that if your resistor is 0, the resistor is not present at all, that is R is equal to 0. So that time these two become equal. Otherwise omega C is always less than omega dash. So these are the two resonance conditions important in the electrical circuit. So far we have discussed these two system. One is a spring mass system and the other is this LCR circuit. So right now we can draw an analogy between them. So let me draw an analogy between them. So one is the electrical circuit and the another is the mechanical system. So both system has a differential equation of this form. So this was corresponding to so yeah. So these were the two terms, that two differential equation for two different system, but the format is almost same. There is the second order derivative and the first order derivative and the term itself, the dependent variable, and the right hand side both has this driving term, that is both are sinusoidal in nature. So let us draw an analogy between them. So for the electrical system, and we have this mechanical system on the other side. So when you compare, you get to see that inductance L is corresponding to the mass in the mechanical system. Similarly, resistance R is corresponding to the resistive force or the damping constant. Damping constant 2B. Similarly, the the 1 by C, that is the reciprocal of capacitance, is corresponding to this spring constant K. And also the current I is the displacement in the mechanical system. And one more thing is this driving force is both of them as this cosine form. So this is the analogy between two kind of system. So this analogy is sometimes very important because with this analogy you can model a mechanical system with as an electrical circuit, and then whatever conclusion you obtain from the electrical circuit can be easily matched to the mechanical system itself. So in real world it's bit difficult to formulate a mechanical system, but easily the electrical circuits can easily since they have this ammeter and this voltmeter give a proper measurement of every quantity. So what we can do is we can set up an analogous electrical circuit for the mechanical system, and whatever quantity that we get to know from the electrical circuit can be easily be mapped to this mechanical system, to the corresponding mechanical system. So we started with this spring mass system. So we started with this underdamped with the driving force present in this spring mass system. So that was equivalent to this LCR circuit attached to AC power source. So AC power source is the driving force involved here. So that's all for today's class. So this correspondence is sometimes very important in physics. Yeah. So if you have any doubt, you can ask me. Right now I'll give a brief recap. So there are few minutes left, so I'll give a brief recap of all that we did. So we started with this like the how to obtain the homogeneous solution to the homogeneous second order differential equation. There were three cases, and then how to obtain the particular solution. So there was this guess method. We were guessing solutions. So we were guessing depending upon what function occurs in the inhomogeneous differential equation. We were guessing various particular solution to the differential equation. So that was one thing that we did, and then we also determined this, introduced this variation of parameter method. That is, we allow the the constant, arbitrary constant that occurs in the homogeneous differential equation to become variable. So we allow this arbitrary constant to become variable, then substituted the entire equation in the differential equation, and like with some modification we could arrive at the particular solution. So that is something we did. And then the next part is we looked at the application of the second order differential equation. One is for the simple harmonic vibration, where we considered first of all the undamped simple harmonic motion, and then we introduced damping term, and next we look at the various categories of underdamped, overdamped and critically damped conditions. And then we looked at if there is a driving force present, which is sinusoidal in nature. So if there is a driving force present, what is the condition of resonance? So we derived that. And also we did a similar analysis for an LCR circuit. So for the LCR circuit, we had this inductance, inductor, resistor and capacitor. They were being fed like driven by this AC power source. So with that we could also write the differential equation and also arrive at the condition of resonance. One is of the current resonance and another is the voltage resonance across the capacitor. So with that what we notice is there is an analogy between the electrical system and the mechanical system. So we mapped various quantities that correspond to each other for these two systems. Yeah. So that's all that we studied in today's class. So in case if you have any doubt, you can ask me right now, or let's meet in the next session to discuss the concepts that we'll be discussing in the upcoming week. Yeah, thank you. Okay, so let me end the meeting right now.